So you just clicked on this video, you saw the title, you probably think you already know the answer to this question. But as it often turns out, the science is more complicated than what we have been told. First, let's take a look at the story we've heard, and why we're so sure that an asteroid impact was a big part of the dinosaurs not existing anymore. I'm not gonna lie to you, it was a really bad day. Sometime around 66 million years ago, a giant asteroid about the size of Manhattan careened into Earth. It smashed into the ocean on the shores of what we now think of as the Gulf of Mexico and caused lasting damage to the planet. The energy of the impact itself vaporized every living thing within a day's walk, then huge chunks of the meteorite that had been thrown up into the atmosphere started raining back down as molten glass. The ensuing cloud of ash and dust that was vaulted into the atmosphere obscured the sun for decades, creating a dim, cold climate plagued by acid rain and firestorms. Over the millennia that followed, at least 50% of the species on Earth disappeared. 20% of the world's species of sharks, rays, and skates, nearly 60% of the plants, 98% of the warm water corals, and of course, 100% of the dinosaurs. For most of us, that collision has become a kind of shorthand explanation for why the dinosaurs disappeared, and because we associate asteroids with extinction, it's a scenario that still scares us. But as our knowledge expands, we've come to see that what killed the dinosaurs, like all of the other great extinctions that happened before, was probably a lot more complex than just a big rock falling into the ocean. Because it turns out, there was more than one disaster movie playing at the Cineplex that was Earth 66 million years ago. It was such a calamity that it literally, in geological terms, marked the end of an era. The dinosaur-dominated period of life that we knew as the Cretaceous era was suddenly over. The new normal, marked by the rise of mammals, would be called the Paleogene era. The giant die-off that created this transition is now known as the Cretaceous-Paleogene Extinction Event, or the KPG for short. And like many things in science, there's not a whole lot of consensus about what caused the KPG, but there are a few facts that everyone agrees on. First, about 66 million years ago, the climate changed a lot. All over the world. We can tell by changes in the types of marine fossils from both before and after the event, along with differences in soil chemistry and other evidence that the climate became much cooler really fast, by 7 degrees Celsius in some places. The transition was so abrupt that the layer of rock that separates the before picture from the after picture is easy to spot with a well-trained eye. It's known as the Cretaceous-Paleogene boundary. And the chemistry of this boundary of rock is itself another weird clue, because it shows up all over the world in the same way. A sudden appearance of a layer of clay that's rich in iridium. Iridium is a metal, and if you've never heard of it, that's because it's very rare on Earth. We tend to find it most often in meteorites and other celestial deposits. The last clue that everyone agrees on is simply extinction itself. Tons of living things just disappear from the fossil record. Tyrannosaurus rex, the biggest land predator at the time, Bennettitales, a group of tall plants with thick armored trunks, and a whole passel of reptiles that lived alongside the dinosaurs and are still sometimes mistaken for them. Aquatic reptiles like mosasaurs and plesiosaurs, and pterosaurs, those freaky flying reptiles. All of them gone. So the reason that the asteroid impact theory is so compelling is that it explains pretty much all of those things. The theory first came about because of that iridium. In 1980, geologist Walter Alvarez was studying clay deposits in Italy that dated back about 65 million years, and found that they contained hundreds of times more iridium than normal. And the more of that stratum of the Earth that he sampled in different parts of the world, the more iridium he found. Since iridium is rare on Earth but plentiful in space rocks, Alvarez and his father, Nobel Prize-winning physicist Luis Alvarez, hypothesized that it was a sign of an enormous asteroid impact. Based on the amount of iridium they found, they figured that the collision was caused by a giant metallic rock about 10 kilometers across, big enough to create an impact with the energy of 180 million megatons of TNT. Clearly, it was a game changer. Alvarez and son theorized that this collision must have been what wiped out the dinosaurs. Soon, scientists started finding other signs of a colossal asteroid impact, like shocked quartz. At KPG boundary sites around the world, the quartz looked like it had been transformed, its crystals rearranged by tremendous pressure that you'd never suspect to find on Earth's surface. Then they found tektites, big teardrop-shaped pieces of glass that form when rocks are thrown into the atmosphere by an impact and then melt on re-entry. So all the signs pointed toward a huge, ugly collision. But there was one thing missing. a crater. Scientists knew about a lot of different impact craters around the world, but none of them matched the magnitude of the one that the Alvarezes envisioned. And then researchers started noticing that a lot of the evidence they were studying, the iridium, the quartz, the glass, was all concentrated in North America. So they focused their search using new technology like satellite imagery and scans that measure the density of rock beneath the surface, and in 1991 they found what they were looking for. A giant crater just off the coast of Mexico's Yucatan Peninsula, about 180 kilometers across, about the size you'd expect a 10-kilometer asteroid to make, and marked by huge disruption in the layers of rock about 66 million years ago. It was named after the nearby town of Chicxulub, and that is how the biggest piece of the puzzle came together. The asteroid impact theory, also known as the Alvarez hypothesis. So like I said, this theory checks off a lot of the boxes when it comes to the evidence we have. Explains the abundance of iridium in the rocks? Check. Accounts for the drastic and sudden change in climate? Check. Was capable of killing 50% of life on Earth? Double check. So the rest is history. By which I mean it became accepted as historical fact, and it's the quick and easy answer to the question of what killed the dinosaurs. Now, you're not going to find many scientists who say that there was never any impact or that the theory is totally off base, but there are many who think that there were other factors at work, and that the extinction might well have started before any asteroid came to finish the job. It turns out, for instance, that the impact occurred in the middle of the most severe volcanic activity Earth has ever seen. India is home to one of the largest lava flows in the world, with volcanic rock covering an area the size of France, and in some places nearly 2.5 kilometers thick. These formations are known as the Deccan Traps, and they were formed by a series of mind-blowingly huge eruptions that scientists think began about 500,000 to 1 million years before the Yucatan impact, and kept going for hundreds of thousands of years afterward. Such violent, prolonged eruptions would have had an unmistakable effect on the climate, sending ash and dust into the atmosphere, obscuring sunlight, killing vegetation, and altering weather patterns around the world. And sure enough, fossils show changes in things like microscopic marine life that suggest a steep dive in temperature before the impact by as much as 5 to 8 degrees Celsius. Now, the big picture impacts of this kind of climate change, whether it was caused by volcanoes or an asteroid, are probably pretty obvious. But the thing is, we're not sure how exactly this led to the dinosaur wipeout. For instance, despite the fact that we think of dinosaurs as reptiles, they probably weren't cold-blooded. But from what we can tell about their physiology, they weren't warm-blooded like modern birds either. So they might have been somewhere in between, or different types of dinosaurs could have had different types of metabolisms, but in either case they weren't able to adapt as well or as quickly to changing temperatures as mammals or other kinds of animals. Another problem dinosaurs likely suffered was simply their own success. They were by far the largest animals on land, and lots of fossil beds suggest that sometimes they lived in dense populations. So dinosaurs were probably competing with each other for food, water, and territory by the time the curtain started to fall. Throw in a tiny little variable like a 7-degree change in temperature and you can see how things would fall apart pretty quickly. While some dinosaurs might have given in pretty quickly to the cold, the plant eaters may have dwindled more slowly as huge swaths of plant life started to disappear, and then, without any herbivores to prey on, the meat eaters began to vanish. But that's just one scenario. In addition to volcanoes exploding and space rocks hurtling toward us, it also seems that the oceans were disappearing, not because of changes in climate, but because of changes in the plates of the Earth's crust. Again, about 65 million years ago, the usually dynamic rifts where plates meet under the ocean floor began to stagnate. It's like the plates just stopped moving. And once they stopped, those rifts began to settle, sinking down into the Earth's mantle. As the seafloor dropped, ocean levels dropped with them. This phenomenon, known as marine regression, completely changed the map of the Earth. Inland seas, like the one that used to run through the middle of North America, disappeared, and more than 28 million square kilometers of land suddenly became exposed in less than 100,000 years. Marine regressions don't happen often, but when they do, they are usually linked to extinction events. Because not only do they remodel life on land, turning shorelines into plains and lakes into deserts, they also wreck everything for aquatic life. Marine regressions cause big changes in ocean depth and temperature and can create huge oxygen-poor dead zones. This is probably why fossils show enormous die-offs in plankton, for instance, tens of thousands of years before the Chicxulub impact. With these centers of the food web gone, it makes sense that other saltwater creatures like sharks and rays and corals, and reptiles like mosasaurs and plesiosaurs would not be far behind. Again, it could have played out in a number of ways. And in a way, it's kind of fun to consider all the different scenarios. Like if the Chicxulub impact had never happened, the world would be a very different place. We might still have a world with pterosaurs and armored trees and me riding a triceratops at the rodeo. I definitely wouldn't do that, let's be honest. I don't even want to ride a horse. A tame, docile old horse. I'm like, ow. No. But even if there were no asteroid, a lot of dinosaurs and marine life would probably be gone anyway. In that case, the Chicxulub impact may have just been the last nail in the coffin. Something that turned an already really hard day into one of the worst days in the history of the planet. The point is, we still don't have one single answer to what caused the KPG extinction event, though we generally talk about it like we do. But the more clues we tease out of the ground, the better we'll be able to understand what could cause such a diverse group of animals that once ruled the Earth to all but disappear. Thanks for watching this SciShow Infusion, especially to our Subbable subscribers. To learn how you can support us in exploring the world, just go to subbable.com/scishow. And as always, if you want to keep getting smarter with us, just go to youtube.com/scishow and subscribe.